Hello everyone, my name is Li Jie. I'm a fourth-year PhD candidate at the Center for Statistical Science and the Department of Industrial Engineering of Tsinghua University. Today, my topic is Statistical Inference for Mean Function of Longitudinal Image Data over Complicated Domains. This is a joint work with Hu Qirui. As the digital economy advanced considerably, image data is frequently appeared in our daily life. Image data is generated by decomposing the image into many small areas called pixels, and each pixel has a value to express its grayscale. Compared with the one-dimensional data, image data has higher dimension and complex structure. Longitudinal image data is collected through a series of repeated observations of the same subject over some extended time frame, such as continuous observations of tomography imaging or remote sensing images. The image data is complicated because it has spatial correlation and temporal correlation, and the spatial correlation comes from the observation values at multiple pixels in a same image, and the temporal correlation is among the sequentially ordered images. Most commonly used method of analyzing longitudinal image data concentrates on linear regression models with related errors. George and Abam proposed a linear model with a separable parametric spatial temporal error structure, although they found the information criteria was highly accurate at choosing parametric correlation functions of spatial and temporal correlation. The risk of model misclassification and the poor performance in inference remained inevitable. George, 2016, applied a above model for longitudinal cardiac image study. Both restricted that a handful of successive images with a small number of spatial locations was collected in limited times, but now image data usually comes in the form of magnitude order greater number of spatial. That is, one image has thousands of pixels and temporal and collected at a very high frequency, such as multiple measures per hour, per day, or even per minute. One interesting example is the continued recording of the surface temperature of the Black Sea. An hourly seawater potential temperature data is recorded on the dense regular grades every 1/12 degree both longitude and latitude over 360 consecutive hours. And this blue surface is the domain of the Black Sea. And in this figure, the red line is the boundary of the Black Sea, and the black dots are pixel locations. That is, at these locations, we observe the seawater temperature data. It's dense and regular grades, since it is measured by the automated instruments. And this produces 360 sequentially ordered images, each consisting of more than 6,000 pixels. And these are 4 randomly sampled images. Functional data analysis provides a novel and powerful approach to dealing with image data. Instead of imposing spatial structure directly, it views image data as realizations of random fields which naturally captures the spatial correlation among pixels. French and Kokoschka developed spatial standard smoother, but they involve time dimension into the smoother. That caused the additional computational burden, and inference also couldn't be conducted due to the lack of theory. Kokoschka and Remher reviewed recent developments related to inference for function defined as spatial locations and consider time series of functions defined at irregular distributed spatial points. But what they focus on is spatially indexed function time series, different from our research objects. What we focus on are temporally indexed images, that is, longitudinal image data with higher dimension and more complex structure. From the perspective of functional data analysis, longitudinal image data consists of a collection of n temporally ordered images eta t on a two-dimensional bounded domain omega, and omega can be divided into several disjoint convex sets. The T's image is a continuous stochastic field equal in distribution to a standard field eta. However, the actual observed data is discrete values of a regular grid of pixels from fields eta t plus random errors. Since most image data is recorded by some automated instruments, we assume that the pixel locations are dense regular grids xij, which forms an array, and ytij is the observation of the teeth image at the location xij. Then the actual data set consists of pixel locations xij, and the observation ytij can be modeled as in this formula, and the eta t is a stochastic field, random field, and the second term is the measurement error. A fundamental and practical issue lies in the estimation of the mean function defined in this formula. We also define the covariance function gxx prime. The eta tx can be decomposed into the mean function mx and the psi tx. Mx is a deterministic function, and psi tx is viewed as a small-scale variation of x on the teeth image, and it is assumed to be an L-square process with mean zero and the same covariance function of eta x. And the Mercy lemma leads to the decomposition of gxx prime, and the eigenvalues phi lambda k are non-decreasing series with finite summation, and psi k are orthonormal bases of L squared omega, and they are eigenfunctions. Then the eta allows the well-known Kofunen-Loewe expansion, and psi can be written in this infinite summation, and here phi k are rescaled eigenfunctions called functional principal components, short for FPC, and psi k are random variables uncorrelated with mean zero and variance 1 called FPC scores. One challenge in estimating the mean function is that lots of image data is collected over complicated domains, even with gaps and holes, such as the black sea domain we mentioned before. It's irregular. So some traditional smoothing methods, such as tensor product, kernel smoothing, or wavelet smoothing, suffers from the leakage problem. That is the poor estimation in the boundary. Thus, we use bivariate splines over triangulation to overcome this problem. Wang 2020 proposed the mean function estimation of image data, but they require that the n served images to be ID replications, not the case for longitudinal. To account for the dependence among the temporally ordered images, we introduce a functional moving average structure. And here, AT prime is a linear bounded operator, and psi t and zeta t plus prime, t minus t prime is a random field. And finally, our model can be written in this formula, and our goal is to estimate the mean function. And here is some basic elements of the triangulation. And here are some denotations. Our method is to approximate the eta t by bivariate B-splines. So here gamma t is spline coefficient vector. But due to the smoothness constraints, we need to solve the least square problem with a constraint. To move the constraint, we parameterize the gamma t and convert it to a conventional unrestricted problem. Then the eta t hat has a closed form. Okay, next I will skip some technical assumptions, look at our main results. And the first theorem is that The infeasible estimator M bar converges at the root n rate to the true mean function M with the asymptotic covariance function g phi xx prime, and the first equation is the uniform way convergence, and the second is a pointwise conclusion. The second theorem is that the M bar is equivalent to M hat. Thus, we can substitute M bar with M hat, and we can construct the 1 minus alpha correct simultaneous confidence corridor for M in this formula. Next are the implementation details about the triangulation selection, covariance estimation, and estimating the percentile. And here is simulation results. The data is generated from the following model, and we construct the simultaneous confidence corridor for the mean function M. And in this figure, the yellow surface is the true mean function. The red surface is the bivariate spline estimator. The upper and the lower surface are the 95% simultaneous corridors with 10,000 pixels. And this figure is on the regular 12 polygon domain. And this figure, the domain is the regular 12 polygon with a square hole. We also make the coverage frequency table. And let's go back to the real data. Also the Black Sea temperature data. We need to estimate the mean function of the Black Sea. And the figure B is a triangulation on the Black Sea domain. And here, figure A is a contour map for the bivariate spline estimator, and figure B is a 3D plot. It's the same figure, but the contour map is easy to show the domain of the function, and the 3D plot is easy to show the real value of the bivariate function. And in this figure, the upper and the lower blue surfaces are 95 simultaneous confidence corridor. The second example is Madagascar surrounding sea. Madagascar is an island country in the Indian Ocean off the coast of East Africa. So this this image is more complicated due to the existence of the hole, and the hole is an island. And the red line is the boundary of the island, and the black dots, very dense, is pixel locations, and figure B are triangulation on the Madagascar surrounding sea. Here is a bivariate spline estimation for mean function. In this figure, upper and lower blue surfaces are 95% SCC. To sum up, in our paper, we propose an oracally efficient estimation of mean function of longitudinal image data on complicated domains, and we also constructed the simultaneous confidence corridors. The next are the reference. Okay, thank you for your attention, and welcome all the comments and questions. Thank you.